This is TWIS. This Week in Science, episode number 850, recorded on Wednesday, November 10th, 2021. Talking science on World Science Day. Hey everyone, I'm Dr. Kiki, and tonight on the show, we will fill your heads with sewage, ski wax, and some worms. But first, thanks to our amazing Patreon sponsors for their generous support of TWIS. You can become a part of the Patreon community at patreon.com/thisweekinscience.
Disclaimer, disclaimer, disclaimer. We all know what is actually driving global warming. As the climate summit continues in Scotland, key provisions were put forth to make real changes in auto emissions. A declarative pinky promise statement was written and proposed for governments and manufacturers and investors to sign. And all it stated is that they would work towards all sales of new vehicles and vans being zero emissions by no later than 2035 in leading markets. 23 countries bravely signed the pledge to do something in the direction of change in the next 15, 20 years or so. Absent from the list of the signees, all of the countries who mass produce cars. Japan, Germany, China, South Korea, and the United States did not sign a pledge to even move in the right direction with a deadline. Meanwhile, some auto manufacturers actually did sign it. General Motors, Ford, Mercedes-Benz, and Volvo, but no other automakers. Okay, Jaguar signed it too, but no other actual real automakers signed it. Partly perhaps because making an electric car would require too much investment in research and development, take too long to get to market by the 14-year deadline, and might be poorly received by the car-buying public. Tesla, of course, didn't need to sign because they already make electric vehicles that they started from scratch making about 12 years ago, which have been enthusiastically received by the car-buying public to become a company valued more than all of the other car companies put together. Before all the excuses are pushed aside, before the lobbyists have gone to bed, before the leaders' jibber-jabbering doublespeak falls silent, hopefully before the canary in the coal mine is an actual canary on a submerged tropical island clinging to a lone branch sticking out in the middle of the ocean, the real solutions for what we need to do will be found right here on This Week in Science, coming up next.
I've got the kind of mind that can't get enough. I want to learn everything. I want to fill it all up with new discoveries that happen every day of the week. There's only one place to go to find the knowledge I seek. I want to know what's happening. What's happening? What's happening this week in science? What's happening? What's happening? What's happening this week in science?
Good science to you, Kiki and Blair.
And a good science to you too, Justin, Blair, and everyone out there. Welcome to another episode of This Week in Science. We are back again. Another week, and it just so happens that this science show, is happening on World Science Day.
What?
Ooh, it's World Science Day.
One day?
Peace.
They just have one day for science?
Yeah.
Just one.
It is World Science Day for Peace and Development. And it is a day that is meant to highlight the significant role of science in society. I think we do that every week. And the need to engage the wider public in debates on emerging scientific issues. I think we try and do that with our audience here on a weekly basis. It also underlines the importance and relevance of science in our daily lives. Again, it's what we do here. We get to celebrate World Science every single week on Wednesdays.
It's World Science Week here, 52 weeks out of the year.
Pretty much. Pretty much. I mean, I'm glad that the UN and everybody else out there in the world catches up with us occasionally. But here we are, and we have all sorts of science for the week. I have stories about taking tiny specific looks at proteins. looking at proteins. And I am also sounding the alarm. Well, I'm not sounding the alarm. Some little insects are. And I've got a bunch of brainy news for the end of the show. Y'all want to stick around for the end of the show brains. Justin, what is in?
I've got a rare Just Good News Tech Edition.
Tech edition.
It's a tech edition. It's a technology thing that's just good news.
That's good.
I've got a Why Humanity is Disgusting story. Tools to research humanity's past, as well as why you need to move out of Florida and Louisiana if you didn't already think you had a good enough reason. I'm going to give you 2 good reasons.
I hear the engines revving out there. Someone's getting out of there right now.
Yeah, I'm actually broadcasting from a drag race course right now.
Very good. Very good. Blair, what's in the animal corner?
Oh my goodness. Why skiing will destroy the environment. I also have a story about penis worms and how they're the original hermit crabs. And of course I have fish rubbing.
Yeah.
So
Fish rubbing?
yeah.
Fish rubbing.
Okay.
You know.
Okay. Yeah.
I'm at some point I'll just stop being surprised.
Yeah. It's been almost a decade.
Yeah.
Of things like penis worms and fish rubbings.
Yeah.
Okie dokie. We're going to dive into this show. But before we do, I want to remind you that if you are not yet subscribed, you can subscribe to us on YouTube, on Facebook, on Twitch. We're TWIS Science over there on Twitch. We are on Instagram. We are on Twitter. We're all over the place on the podcast directories. Look for This Week in Science. That's how you find us pretty much everywhere. And you can find our website at twis.org. Now it's time for the science. Okay. Let's talk about bias. We're going to talk about bias in science. In an area that you probably weren't thinking that there would be much bias. Telescopes. I'm not talking about diversity, equity, inclusion. I'm not talking about social justice. I'm talking about the way that telescopes look at the plane of the Milky Way and the way that telescopes are able to see or not see through dust in the Milky Way. Researchers have never been able to detect black holes more massive than 20 times the mass of the sun. There is and I think I've mentioned it before on the show, there is what's called a stellar graveyard of solar masses. There's a place at which we just can't find anything. We can't get past it. And hypothetically, we should be able to. Hypothetically, if stars are exploding and turning into black holes, then black holes merge with each other and more mergers happen. We should be able to see these big, giant mass black holes with lots of gravitational pull. Like, we should be able to see them and see what's going on. But we're not. We're not seeing anything of over 20 solar masses. So what's going on? Well, some researchers were recently doing an analysis, and they have determined that when black holes are formed from stars that are the size to go supernova, the force of the supernova jolts the black hole, and that black hole can move, and the material around the black hole can actually be pushed out of the plane of the Milky Way. However, when a black hole is so big it just implodes on itself, that implosion doesn't lead to the same forces that the supernova does. And so these giant black holes aren't getting bounced around, and they are sitting in the plane of the Milky Way in which we're sitting, and they're surrounded by dust and gases that we can't see through with our telescopes. So they think that with telescopes like the James Webb Space Telescope that is set to be launching here very soon, hopefully December-ish, We'll see if that happens. But that space telescopes that see in the infrared would potentially be able to see past the dust and the gas that's in the way. And we might be able to actually test this hypothesis that there are these larger black holes out there. We just can't see them because our telescopes are biased toward things that are visible.
Okay. So, but this is confusing me a little bit. So these are black holes within the galaxy.
Yes. Within the galaxy.
We've discovered there are discoveries of black holes much more, billions of times, billions of solar masses. Okay, yeah, just want to be clear.
There are giant black holes outside of our galaxy,
ultra-massive
our galaxy.
Billions of solar masses out there that have been discovered. But yes, within our galaxy, there's a limit based on this not being able to penetrate through dust or something. Okay.
Yeah, thank you for clarifying on that. Yes. Yes.
Well, because it made me like it made me think. Every once in a while, when anything comes to cosmology and physics, there's a point where I'm like, "Oh gosh, you mean that you just theoretically believe that these things exist based on probably gravitational movements of a solar system that's a billion, zillion, trillion light years away, whatever." Right? Okay, that makes more sense.
Sorry to have confused you. I probably confused more people out there too, who are like, wait a minute, we've seen these things. Yes. But this stellar graveyard, it's like a gap in our knowledge, in our galaxy. But it shouldn't be a gap. But it's probably just because our tools have not been appropriate for being able to see the things that we want to see. You can't see it until you can see it.
Mm-hmm.
Right? Yeah. So anyway, there's a lot riding on the James Webb. We hope that it launches and actually works. Yeah. So, yes, it will be coming. It will be coming. Justin, what'd you bring?
Just good news, everybody. Tech edition. Engineers at Lancaster University, working with the Josef Stefan Institute in Slovenia, have successfully transferred digitally encoded information wirelessly. That's not new, you say. They used fast neutrons instead of electromagnetic radiation used by cell phones, radio, and Wi-Fi systems. So they use these fast neutrons, and all of their transmission tests proved to be 100% successful. It just worked. And they're like really ecstatic about this, of course. Fast neutrons have an advantage over conventional electromagnetic waves, they say, because of the traditional conventional electromagnetic waves that we use. Those frequencies are significantly weakened by transmission through materials, especially metals. This could allow cell and Wi-Fi signals to reach places currently that may have issues, such as deep underground. You've probably experienced it in a parking structure. Maybe you work at a bank and you're in the vault and you lose cell signal. But you can also just within a home be on the wrong side of a thick wall or concrete wall. Maybe you don't get to Wi-Fi out into the garage. So this could be a solution to that. May even be able to open up in the future the digital spectrum that we're using, which is continually being congested, where we've got all these different electromagnetic signals and you have to have these frequencies and widths of band that are available by creating a new fast lane in wireless communications by utilizing this. They also hint that it could be used in materials, testing bulkheads of ships, maybe the propellers of an airplane kind of a thing, where you can go in and test those materials the way we do now, looking for defects and that sort of thing. That we currently use electromagnetic radiation for. The researchers sourced the fast neutrons from californium-252, which is a radioactive isotope produced in nuclear reactors, making the waste from a spent nuclear fuel potential material for our future electronics. So that's good news.
Nuclear waste?
Yeah. So, nuclear waste.
I was waiting for the catch there for the just good news.
No, it's just good news. I mean, if you think about it, we keep talking about all these bandwidth issues, and there's so many digital frequencies that are out there now, and we're like, oh gosh, you got these, and then how do you maintain all of these these little bandwidths of energy. If you have this other one that's using a completely different transfer system, penetrates the wall, so you won't have that weak spot in the other side of the garage on your cell signal, or if you work in a large building or whatever it may be. These will penetrate through the walls and that sort of thing. And they're apparently very efficient. They may also be able to be used coupled with traditional signal, so that you could have both operating at the same time. And
that sounds like it would be useful.
Yeah.
Yeah. So you get more multi-band kind of data.
Yeah. And it also could work as a confirmation bias if you're doing a very sensitive data transfer or something like this. So there's a bunch of uses potentially for it. And we keep running into these material shortages all over. We have plenty of nuclear waste around. Plenty. You can just pop those in your cell phone. You'll be fine.
Yeah, right.
Mm-hmm.
Everybody wants some nuclear waste in their cell phone.
Yeah, they did.
Right up my face.
Well, so
the
thing they point out,
You're glowing.
There somewhere in this study is that the frequency, the rate that they were using the signal itself, was not harmful. There may still be an issue. They don't go into it, of course, but in the materials that are being used to produce. Yeah, it's a future people problem. And people are really good at solving problems, so it'll be fine.
Oh yeah, gotta go restart the router. Let me get fully suited up. Open up the concrete box.
I don't want to do it. We're not going to do it that way. Okay, Blair.
Yes.
Where do you want to take us now?
Here's my own just good news, I suppose. Blair's good news. I don't know. My name doesn't do the same thing. We were talking last week about how skiing is ruining, how skiing is going to go away.
Gonna go away. You're gonna have to learn how to ride a mountain bike.
Yeah,
if you like
that's great because skiing is actually really bad for the planet. This is from the Norwegian University of Science and Technology. It turns out that ski wax is releasing fluorine-containing compounds called PFAS into the environment. Mm-hmm. Now, I just saw, shameless, this is not an intentional plug, just this is where I saw it. There's an awesome piece on PFAS on John Oliver recently, talking about these environmental toxins and how they impact humans. Well, so that was coming from things like Teflon, pipe coatings, other things that are in our lives.
Interior of all packaging, basically.
Yeah.
Everywhere.
So it's also in ski wax. And so in Norway, it's getting into the soil and into the worms. It's ending up in the environment and it's getting eaten by animals. And so by ingesting PFAS, the voles in that area had high levels of PFAS in their bodies from eating the earthworms, along with high levels of neurotransmitter of dopamine in their brains. They also had low levels of testosterone. So then they took some mice, they fed them some high PFAS in the lab, and they found out that half of that was true. The PFAS was indeed causing dopamine problems. The dopamine system was affected in mice receiving PFAS in the lab, but there were no changes to testosterone. So they were able, through this long, very interesting study, they found out this PFAS is impacting rodents. It's a problem. It also potentially is messing with their livers. It's giving them enlarged livers, which is really interesting. They don't know exactly why that is. But they know that these things could have serious consequences. What's interesting is they think there's actually a different environmental toxin causing the testosterone changes.
Oh, wow.
So there's more than one.
Yeah. So there's something else going on, too. The PFAS is causing the liver and the dopamine problems, but there's something else causing the testosterone problems. So the soil's just all messed up. But ultimately, this can have behavioral problems if the dopamine system is messed with. So it could lead to disturbances in fear and anxiety, thermoregulatory processes, the ability for them to protect themselves, their ability to woo and reproduce. It also can cause mood swings and can cause motor and cognitive challenges. So all that to say, these chemicals that people put on their skis, they are chemicals. This wax, it's not pure beeswax. There's other stuff in it. that is going to end up in the environment if you're skiing. So that's something to keep in mind. And then immediately I was thinking about surfboard wax. There are all natural surfboard waxes out there, but not all of them are, I'd be willing to bet. So this is a good reminder that whenever you're spreading a chemical onto something and going into the environment, it ends up in the environment.
Yeah. I think it's already in everybody's blood, right? This is one of the
PFAS,
things. The PFAS. It's already in everybody's blood.
Mm-hmm.
There's they had to actually, to get a sample of blood to compare, they had to go and I think they had frozen Korean War veteran blood samples that were
before
taken.
plastics were available, before we were lining cans with this material, and
that was the only clean sample they could find.
Yeah.
Yep.
In human populations that didn't have this in there to some degree.
Yeah, and I think that's a good reminder that this isn't just affecting voles and mice. Any chemicals we put into the environment eventually comes back to us. We're not isolated. So
we need to remember, it's the things we put into the environment come back to us because we're part of the environment. And when there are chemicals in everything, right? There are chemicals in the environment. There's chemicals, but we are creating chemicals through our chemical industry that have been separate kind of in this own little world they were derived separately from an involvement in nature. They weren't this is great.
No, this
for
is completely man-made.
We've synthesized things. It's look what that does. That's great. Let's use it for that. Not knowing at all what these compounds can or would get up to. So, as we move to the future,
there was actually, we're talking about a thing that's not in this story, but there were industry reports that were warning about that from the researchers working for these companies that were like, hey, we should be very careful with this thing that we created, not to let it get into the environment. And the researchers were ignored because there was corporate interests.
Yes.
Huh.
Well, TWIS didn't exist yet to interpret the scientific studies that came out. So, we're here now.
Yeah.
Well, thank goodness we are here now to interpret these things. Other things that need to be interpreted are our entire bodies, the things that make up our bodies. Justin, you've done a lot of work on the with the nanopore DNA sequencing or a bit of work in your genetics work with some of the new DNA sequencing technologies. And the nanopore stuff is really amazing because it's these basically a pore. It's a space that allows, it's an ionized space that allows a single base from DNA to go through it to be read. Oh, when it passes through the electrical signal that gets the charge that goes past through the pore, you go, oh, that's a guanine. Oh, that's a thymine. You can identify what it is. And it's been amazing at revolutionizing the speed at which we're able to sequence DNA and see sequences of DNA, what they're made up of. So some researchers...
Speed and the length. It's also able to do much longer reads with a decent degree of reliability.
Yeah, so it's great reliability, right, and speed. And so it's making a lot of the sequencing work that we're doing very efficient. Researchers from TU Delft and the University of Illinois have adjusted it very slightly so that the technology doesn't read DNA in this new incarnation, but rather protein sequences.
Yeah,
so what they have done is shown a proof of concept and read a single protein molecule. So basically the string of amino acids that make up a protein, and have been able to read the electrical signals and identify. They have shown that they are able to identify single base mutations within single amino acid mutations within the protein sequences. And what this means is that it could lead to an ability to read our proteomes, that this will allow us to really identify the proteins that are active within our cells at any moment in time. which is a huge question of interest because we don't know. We know that things happen environmentally, our bodies change, stressors, whatever, and that leads to a cascade of events that lead to protein transcription within the cell. Proteins get created and the proteins cause certain functions to happen. And what are all the proteins that are involved? How are they working? What do those proteins look like?
They're doing all of the work. They are all of the how stuff is taking place within a cell. And so, and throughout the body. And so it is one of these weird things where we think we have learned so much about anatomy and, medicine and all this, but all we really have ever had is a very high altitude overview of cause and effect.
Right.
Like really, we really, the mechanics of everything and the level that it's taking place is this proteomic level. And we have ideas generally about what's happening, but we don't have a high definition view of it that allows us to identify so much of this field. It really is just at the beginning of being open. If you're like, oh, I don't want to research medicine, human anatomy, they've already figured out you got a heart and a lung, 2 lungs actually they found, and then there's like a liver. There's so many more layers to the point where we're really only breaching the subject.
Yep. Yeah, the controls and the processes, how everything works within our cells there's so much still to be learned. And this tool could become incredibly useful in the same way that the nanopore technology has opened up DNA sequencing to so much investigation in recent years.
And the other thing that we're likely to learn from this is going to be probably a little bit disturbing.
Oh, yeah?
Yeah, it's that whatever the rules are, whatever the construct is that we've built for how biology works, it's going to be biology, which means, like you're saying, you can identify the nucleic acid difference between one protein or a change over time or something like that. That's actually taking place all the time, everywhere in the body because it's biology, which means even all of the things that we learn are tied to the fact that we saw it once or twice or generally accept that this is what's happening and this is what's taking place. But on the biological level, things are always changing.
Yep.
Differences are always taking place from one human to another. The cells, those protein structures might be slightly different. And so how does that affect human health? How does that affect an immune system? How does that affect the upper scale echelons of categories? It's an intense field that, again, if you haven't picked the thing to study and you kind of like, maybe biology, but this is like an incredible, cell biology is going to be an exploding field over the next decades, I believe.
It's absolutely going to be. And yes, to answer Aaron Lohr's question, it means they can detect amino acids. Amino acids are made from combinations of 3 nucleotides from DNA. So when proteins are transcribed and translated, you have the DNA, which has the nucleotides. The nucleotides are then transcribed, copied via RNA. That RNA is a sequence of 3 opposite nucleotides to the DNA sequence, or I guess their partner nucleotides, the complementary nucleotides. The mRNA that comes from that gets transferred to the ribosome. The ribosome then turns each group of 3 nucleotides into an amino acid because it's like our Morse code, or it's our code book. There are combinations of nucleotides that code for specific amino acids. And this technology will not identify nucleotide mutations, but will identify amino acid changes, which is still important because that means that there's been mutation and that there's been a change somewhere along the line. So, yes. Okay. And you have a science question related to that someday. If you have science questions, everyone, you can send us science questions. We do like them. Justin, what's your next story?
I don't know which one I actually have queued up next. Let's see. Oh, yeah. Humans are disgusting, according to researchers at the University of California, Santa Barbara. with the Columbia Climate School, they published in the open access journal PLOS One a high-resolution map of nitrogen and pathogens released into coastal ecosystems from human wastewater. To capture the impact of human sewage on coastal systems, these researchers mapped estimated nitrogen and pathogen inputs, and that's outputs from land, inputs into the ocean, from sewage of about 135,000 watersheds around the world, resolution of about 1 kilometer. The assessment employed newly available high-resolution data on global human populations, modeled how wastewater plumes entering the ocean would overlap in different ecosystems. Of the watersheds that appeared to release the most nitrogen from sewage, most are located in India, Korea, and China, with the Changjiang River contributing 11% of the global total. That's more than 11% of the humans in China, so that kind of figures. The researchers also identified hotspots for coral reef exposure to nitrogen in China, Kenya, Haiti, India, and Yemen. Seagrass exposure hotspots in Ghana, Kuwait, India, Nigeria, and China. Seagrass being a foundational coastal habitat, many parts of the world, not kind of important, really very important to the health of a coastal system. If they go away, also then the erosion tends to scale up. From the authors, they're saying the sheer scale of how much wastewater is impacting coastal ecosystems worldwide is staggering. But because we map wastewater's inputs into the oceans across more than 130,000 watersheds, our results identify target priority areas to help marine conservation groups, public health officials work together and reduce the impacts of wastewater on coastal waters across the planet. There is a map, and you can always zoom in that map too to find out if your local coastal area is imbued with quite a bit. Go! If you look at the waters surrounding Manhattan or off the coast of Louisiana, there's some really... Oh, Baltimore Harbor? Do not go into harbor water. No, stay away.
I feel like this should be one of those horror movie promos where it's like, don't go in the water.
Yeah, don't go in the water, because it turns out the water, the world may be your oyster, young man or woman, but it's also everyone's toilet. So we should learn how to manage how and what we flush into it a little better. As long as we've all agreed, maybe by default, that the ocean is going to be our toilet. And to be fair,
it is fascinating looking at the map, though. It's really interesting to look across the coastline, and it's like every what would be an outlet for every river and stream system, which are used across the country as sewage effluents. Here in Portland, all of our sewage, especially if the water, if it rains a lot, the sewage gets overflowed, and the overflow is into the river, and that's going to head out to the Pacific Ocean. And that's pretty much everywhere, but fascinating.
But it's, off the coast of Los Angeles. Yeah, that's looking rough.
LA, you got some trouble down there.
Yeah,
Take care of your...
Don't go to the beach. Stay out of the water on the beaches. It's
San Francisco Bay, not looking great.
Bay is not a place you want to fall into.
Not looking as bad as LA outside of the Bay, but the Bay is not.
And what's sort of interesting too about
agriculture runoff as well. It's not just going to be sewage, because you've also got fertilizers and a lot of the ag industry that's going to be adding to this.
So for the global output, at least, about 32% of it was from agriculture. The rest is human sewage and waste. Okay. So it's mostly us. It's mostly, it's all us. Actually, it's 100% us. But, and I think overall, it's not an issue of the ocean not being able to handle nitrogen. The big issue is that we're just dropping it on the coast.
Yeah.
And it's, that's our coastal habitats is where, is going to absorb less than it's going to disperse. So maybe just we need longer pipes to go out further into the ocean. I don't know.
So
Global sewer system.
I'm seeing two things on this map. So one is there's obviously in highly populated areas, there's some bright green, there's some toxic green. But the other thing that's really important is topography and fluid dynamics in those spaces.
Yeah.
So the reason that the
sure.
San Francisco Bay looks like the way it does is because it's basically the bathtub drain through the entire watershed.
Central Valley. Mhm.
Yeah. So it's the entire, all the water coming down from the Sierra Nevadas from 3 directions collects there. So of course it's all going to collect right there, right?
Yeah.
And it does, the bay does a really good job of filtering through all of that, which is why you don't see it on the outside. So it's also a good reminder, aside from just knowing that populated areas are gross, that when we consider our pollution of all sorts, that the dynamics of the topography of the space should be considered, because it's going to go where it's going to go.
Right. Yeah. And that's what this modeling tool is designed to help with, so that you can see where, you have collection areas or high density areas that you can either mitigate on land or just monitor on those coastal areas to make sure that it's not having too negative of an effect, because it's gonna, have some kind of a negative effect. If you consider the land on the earth, and all of the creatures upon it, and then see that it is basically lined with a bathtub ring of sewage from one species, it's kind of actually impressive what we've done to the
Nice
earth.
work, humanity.
Left our mark, literally.
Yeah.
Not the way I wanted to. Oh my goodness. But there are other things that leave their marks as well, and you have to sound the alarm to ensure that they don't have a terrible effect before it happens. There is a specific alarm sound that I'm going to play right now for you. This is the sound. Honeybees.
Yeah, danger in the hive.
Very upset.
It's a grumpy bee.
Very grumpy. This is a beehive. It's a honey bee hive, Apis cerana, from a beehive where in Asia, Vietnam, where the murder hornet originated. And this giant hornet, Vespa soror, the scientific name, has invaded North America, but the bees here don't have any adaptations to defend their hives. This particular group of honeybees has developed, we talked previously about the ability of smearing mud on their hives to mask the scent of the hives to protect it from these giant hornets. And this new study, these researchers from Wellesley College have published in Royal Society Open Science, their study of a hive colony that they have detailed this harsh, irregular, shifting frequency call that is unique to the response to this hornet specifically. So the honeybee has adapted a new response in Asia, in Vietnam, to rev the colony up to bring honeybees to the doorway of the hive so that those honeybees can start increasing the temperature locally, blocking the entrance, spreading mud on the entrance, so that the amplified call is like the time to go to battle. We must get to our defenses. Yes.
Yeah, bees are. More we find out about bees, they're just great communicators.
Amazing communicators.
Yeah.
I wish I could communicate as well as some of these honeybees some days. Sometimes it doesn't come across quite so clearly. But I do hope that we're coming across loud and clear right here. This is This Week in Science. Thank you so much for joining us for another episode of The Science. If you are enjoying the show, please be sure to tell a friend. And head on over to TWIS.org and get yourself a new 2022 TWIS calendar. There's Animal Corner calendar. They are available now. TWIS.org. Click on the toad. Order your calendar today. It's time for our COVID update. Yes. All right, let's boopity boop into a question that has been posed by many people. The idea of whether or not COVID is seasonal. Will it become seasonal? What's going on? Well, there's a new article on thescientist.com looking into a lot of the research that has gone on. And really, the evidence isn't clear. It doesn't appear to be so very seasonal in nature. It is affected by temperature and humidity to some degree or another, and that does seem to affect it. But really, the larger effect comes from human behavior. And so the take-home message is that it may yet become a seasonal virus, a seasonal disease similar to the flu that is a virus of the winter, at least especially for northern hemisphere countries and or countries that are closer to the poles. But really, it's as the virus becomes endemic, it really depends on treatments, vaccines, human behavior, and what happens to the pockets of the virus as it becomes just around all the time.
So one of the things that's also about seasonal outbreak is that it's not like, oh gosh, hey, it's winter now. You know, the cold virus is it's more active. Going to get out of the house a little bit more. It's because these are times you're like, we're going to see a spike. Post Thanksgiving, post Christmas. We're going to see a spike as families and groups of people get together in close quarters and break bread and tell each other that they love you. It's great seeing you again. And they're coughing on each other and they're sneezing on each other. And then malls, this is the thing I always bring up because I find it fascinating. Malls, which isn't as big a thing anymore as it used to be. People still go to them for the shopping season. They're not heated in the winter. It's just the humans walking through. They just turn off the air circulation in the winter in these big mall buildings because the humans walking around actually are enough to warm it up. But that also means you have congested airspace with lots of humans in it. This is part of what seasonal outbreak is about. It's about people who are no longer distanced. So we're going to continue to see continual infection as well as seasonal spikes. It's actually both.
I've taken, instead of just saying like, oh, now that COVID's getting better, or once COVID's over, I say, now that COVID has become endemic.
Yes, and that's the key because it's not going away. And I just was reading some tweets today from Andy Slavitt, who used to work with the White House and has been doing some great science communication work with respect to the pandemic. And he said, a bunch of people are saying the pandemic is over. Like smart people on media are saying the pandemic's over. It's not over. And even though you might be vaccinated, your local community may have very little spread. There are still pockets. There are still places around the country, around the world where the virus is still very much a problem. Across the United States, we are still seeing, 1,500 deaths a day. We are seeing numerous cases. The Central Valley in California is experiencing an increase in cases, which is a concern. There is a concern among epidemiologists as to what's going to happen over the holidays. But all you can do right now is keep it, be aware, be compassionate, be aware, and don't rub the pandemic being over in people's faces because it's not over yet. And it may or may not become seasonal. It all depends on us.
It depends on the least of us. The least willing to follow guidelines and do social distancing. Took the kids to the zoo. This is a personal story. Took the kids to the zoo the other day because they had a dinosaur exhibit, which was really fun. Plus, it's the zoo, which is always awesome. And there's you have to wear the mask at the zoo. Dozens of parents out there not wearing their masks.
Mm-hmm.
These are the people within our society who are going to make this endemic and these spikes and the rest of this, because there's people who just don't get rules that are in their own interest even. I mean,
throw your trash in the garbage can, people. Come on.
Yeah, don't litter, don't
pee in the
smoke on an
pool.
airplane. You can pee in the pool. That's fine. Plenty of chlorine. But can't you? Isn't that fine? Peeing in a pool can't be that big of a problem.
All right, moving on from whether or not it's seasonal. Researchers have taken a different kind of look at the Delta variant of the COVID virus, SARS-CoV-2. And what they have used to investigate it, as they've published in Science this last week, is what they are calling a viral-like particle. And they are using these viral-like particles to investigate contagious viruses without actually using the whole virus. So what they do is it contains the virus's proteins, but not the virus's genome. So there's no RNA genome. And so the particles can attach to cells. They can start to inject into cells, but they can't infect cells. They can't use cells as their photocopier.
Right. That's basically the two parts to a virus. You have that shell, and then you've got the little bit of RNA in the side that then, once it gets into a cell, is the thing that takes over that cell's normal system and replicates its DNA and then makes more virus.
It's all white, no yolk.
But this is this is all eggshell. And how does the eggshell get in there? That's a smart way of doing it.
Yeah, and so they created a copy of the Delta variant with the particular R203M variation. And so, I'll go back. So they created this particle, and then they started playing with it to figure out what aspect of the virus-like particle allowed transmissibility. They found that a mutation in Delta's N protein, which is the nucleocapsid protein, which is the protein that encases the virus. It's called R203M. And this particular mutation in the nucleocapsid is the one that allowed increased transmissibility. It increased the amount of RNA from the virus that would make it into host cells. And so by looking at this, they mutated it, they tweaked it just a little further, and they found that they could still mutate that nucleocapsid protein further to make it more transmissible. So they weren't messing, this isn't gain of function. They didn't mess with a real Delta variant SARS-CoV-2 virus, but this virus-like particle that was very, very close to being Delta, they showed that Delta has the possibility of becoming even more transmissible than it is now.
Oh, gosh.
So what can we do with that information?
Run.
No. Yes, this is a great question, Blair. What we can do with this information is that we can use it to design treatments, to design vaccines, to design antivirals that target not just the spike protein, but this part of, or just in general, the nucleocapsid. So this N protein of the Delta variant we've seen is very important, and that is one that we should be looking at for our future developments of the drugs that we use.
Sounds like a smart system.
Yeah. So the reality is, like, even if this nucleocapsid, the N protein, did mutate further, there's no absolute promise that it would actually work better in practice in nature, because this is just a very specific example in a dish. And so we don't know the dynamics of how it would, or if it would actually change transmissibility. But in this laboratory dish environment, it did work. Yeah, so they tested live coronaviruses mutated with this R203M on lung cells and found that these viruses induced the cells to produce 51 times more virions than the original strain of virus.
Oh, no, that sounds bad.
It's really bad. You guys, let's get vaccinated, wear your mask, social distance, don't pretend the pandemic's over because it's not, and this virus could get worse, but it hasn't yet, so I don't want to panic anybody here, but just put it out there. Scientists, please start looking at the nucleocapsid some more and create your treatments there. We want them.
Frumpy B in the chat room is pointing out that Singapore, which has universal health care, they have one payer says you don't pay anything for your doctor in Singapore. Yeah. Everything's covered. They are going to start charging people who are unvaccinated who go to the hospital with COVID-relatable stays, which is a pretty interesting thing because the thing that made me think of that story that's out there that they're proposing, it made me think of this really interesting Venn diagram of people in the United States who can't be dropped by insurance for a pre-existing condition of having gotten COVID without having gotten vaccinated. And those who are, and they're going to be able to keep their health coverage because of Obamacare, even though politically, many of these same individuals were totally against the thing that now is going to allow them to not get dropped by their insurance companies for having gotten COVID. So I think that's there's a lot of interesting healthcare related issues and cost of healthcare related issues with the unvaccinated holdouts.
Yeah, but there's a story that Fada shared as well, which is that in speaking of the vaccines, though, in France, France is recommending that people under 30, boys under 30 years of age, do not get the Moderna vaccine because of the higher likelihood of myocarditis. And it seems as though there is an even higher likelihood of myocarditis with Moderna than there is with Pfizer, which is a concern. But again, if you know that it's within certain age groups, we can manage that. And Blair,
what I wanted to talk about was actually the vaccines you should have been taking over the last 2 years that maybe you didn't because there was a pandemic on. So this is a peer-reviewed publication coming out in the American Academy of Family Physicians, reminding everyone that there is a severe disruption to routine vaccination services. And so that deficit needs to be recouped quickly, or there is the potential for a strain on the already overtaxed health system, and there would be dire consequences for future public health. So this is things like, what else is bad besides COVID? Oh, just, measles, mumps,
measles,
diphtheria, tetanus,
what about
polio,
that whooping cough? What about that whooping cough? I hear that's
HPV.
terrible.
HPV. These are all things that we normally get shots for when we go to the doctor every year.
But we haven't been going to the doctor.
We haven't been going to the doctor. Right. And honestly, I'm kind of worried about the fact that there were lots of people out there that were told it was time for their annual shots. And they got their shots. And now they're going to hear the word vaccine, and it's going to be a whole thing. So I will be interested to see from a sociology standpoint if normal routine inoculations in some cases drop because of the politicization of...
Such an easy word to say.
Of vaccines over the last couple years.
Is that a good word? I think it's the ignorization.
Sure, but it is aligned
accurate.
with a certain identity is the issue, which is what that means, right? So this is part of it is feeding into identity politics so that your desire to take proper care of yourself medically is now somehow tied to your value system, which is a strange world that we live in. But I just want to throw out there, if you haven't been to a doctor for a while because of COVID, you're vaccinated against COVID. Hey, guess what? Make an appointment. Go see your doctor. Make sure you're up to date because
the flu is still here. The flu,
go get your flu shot.
We have to watch out for the flu if they're, everybody needs to take care of themselves.
Shot, double mask, go to your doctor, get your vaccines. If you don't know if you're due for some other vaccines, send them a message. I know most doctors now receive emails or some sort of secure message system, or you can call them on the phone. Find out if you or your loved ones need vaccines and go get them, because COVID is not the only vaccine that you need. That's all.
That's good. That's good. Thank you. There are so many things, and we forget because some things they're baked into our routines. And when the routines got messed up, it all got messed up. So hopefully we'll get back in those routines again. Everyone will take care of themselves, take care of their communities. Let's work on community immunity and keep moving forward. This is This Week in Science. Thank you for joining us for yet another episode, spending your time with us today. If you are enjoying the show, please head over to TWIS.org and click on that Patreon button. We really would appreciate your support to keep this show going. The Patreon button takes you to our Patreon community where you are able to choose your level of support, $10 and up per month. You get thanked by name at the end of the show. And we also have calendars available. Let TWIS help you keep track of 2022. Head over to TWIS.org, click on the toad, and order a calendar today. Thank you for your support. We really can't do this without you. We're coming on back. Coming on back.
Hey, what time is it, Kiki?
Coming on back. It's This Week in Science, and it is time for Kiki's jazz songs.
Yeah.
No. Boom. All right, it's time that we all wait for. Blair's Animal Corner.
With Blair!
She loves our creatures, great and small. Biped, millipede, no pet at all. If you want to hear about animals, she's your girl. Except for giant pandas and squirrels. There's Animal Corner.
What you got, Blair?
Oh, I have a lovely story about the prehistoric Priapulida, aka the penis worm.
Ugh.
Researchers from Durham University and Yunnan University reveal that penis worms, Penis Priapulida, invented what we now call the hermit crab lifestyle some 500 million years ago at the rise of the earliest animal ecosystems in the Cambrian period. So just after the Cambrian explosion, the penis worms found a way to take care of themselves amongst all these new predators. Hermit crabs are well known for using snail shells and other shells as shelters against predators. One of my favorite things about them is how they'll actually line up in a row from biggest to smallest and trade up in their shells, since they grow out of the shells over time. It's very cute. Well, it turns out that penis worms may have come up with that on their own ahead of time, hundreds of millions of years before the hermit crabs. And this is all discovered because of the Guanshan fossil deposits. These are famous because they preserve some soft tissue. And so there were fossils that had both the bodies of the soft penis worms alongside a shelly material that made up this specific fossil record. And so they found 4 specimens of these worms, Eximipriapulus, and they were found inside conical shells of hyoliths, which basically just look like ice cream cones. It's really the only way I could describe it. And so they're a long extinct fossil group, but they're an invertebrate that lived in these big cone-like shells. And so when they would die, it appears that the penis worms would live inside these little ice cream cones.
Except for the little bit that was melted out of the cone.
Yeah. So they're always, in all 4 cases, they were sitting snugly in those cones. In the same position and orientation, which led researchers to believe it was intentional. Of course, after the Cambrian explosion, there were many aggressive, voracious predators, and the soft body of the penis worms would be a perfect bite to eat, essentially. And so they were able to take permanent shelter in these empty shells, so they suspect. This is the only explanation that made sense based on the orientation of the worms in the shells. And that is that it was their homes. And so this is very cool because there's this complex ecology developing immediately after the Cambrian explosion. Something that this kind of complex behavior, do you want to call it tool use? I don't know, you could. But this is something that you usually consider to be from much younger geological periods, animals that are quote unquote smarter than that. And so this hermiting lifestyle, this is the earliest it has ever been documented, of course, and it has not been directly observed in any living penis worms. So this is something that it seems like they did very specifically during that time. And so that also highlights the remarkable speed and flexibility of evolution.
It's so fascinating.
I'm just being a worm. I'm just
these
nice
old
and
worms.
fleshy,
They're soft-bodied. They could be eaten.
Oh, what's that? Better hide.
Right. Something's going to eat them. They want to hide. But they're probably not thinking too much, but they probably figured out that these shells, these things were protective. Or the ones that were in them didn't die.
I mean, think about like sea cucumbers. They're not, they're even less evolved, quote unquote, if you want to think about nerve nets and things like that, than worms. And they know to go into areas of tide pools that are harder to reach. They know that. And I don't know if it's because of shade or proximity. They can feel it's kind of close in there. There's stuff around them. So there's some sort of sensory information that these worms are getting that know they're in a tight, hard space. And that means that they're protected.
It's like they have a mind of their own.
Yes.
But these are fossil from the Cambrian, right? So this is millions of years old. Do any of these penis worms hide in, or do they act like hermit crabs today?
None.
Okay. Yeah. Interesting.
So that's why it's so wild. Yeah, they
Yeah.
lost it. They didn't need it anymore. I don't know.
I don't need a shell. I can make it. I'm tough.
Yeah. And now moving on to fish rubbing. So this is a study from the University of Miami Shark Research and Conservation Program at the Rosenthal School of Marine and Atmospheric Science. And they looked at fish chafing, which is exactly what it sounds like. It is a cross-species behavior where fish rub up against other animals, and in this very specific case, sharks that could eat them. So their research found this was frequent, widespread, and could play a previously unappreciated ecological role in aquatic ecosystems. They examined underwater photos, videos, drone footage, and witness reports and found 47 instances of fish rubbing against shark skin. They were documented in 13 locations around the world, and they varied in duration from 8 seconds to over 5 minutes. They recorded 12 finned fish chafing against 8 different species of shark, including great whites, and in one case, they documented silky sharks chafing on the head of a whale shark. And the number of fish chafing against sharks ranged from 1 to over 100 at a time.
Wow.
What is going on here? Chafing has been well documented between fish and inanimate objects like sand, rocky substrate, but chafing against sharks, something that could eat them.
Right? But sharks have the amazing tooth-like skin.
Yes.
And so here's
skin would be an amazing exfoliator.
Is that what's going on? Because if anybody who's just listening, what we're seeing is images of sharks, sort of swimming through the ocean, and these smaller, like feed fish, just like side bumping up against them repeatedly,
Bump.
hey buddy, like nudging them. So is that what they're doing? Are they exfoliating?
Great question. Don't know. Would have to do a study where like you removed all the dermal denticles from a shark and then figured out if they still want to do it. But it seems to be the best reasoning behind what's going on.
And now the images you're showing now, Now it's the sharks that are doing
On a
this
whale shark.
to a whale shark.
Yeah, so shark on shark, yes.
Yeah.
And so on a whale shark, there's not a lot of risk to it, really.
Danger. Yeah.
But anyway, but yeah, shark skin covered in dermal denticles, basically skin teeth, and they have this really rough sandpaper surface. So the researchers' theory is that the chafing actually helps them to remove parasites or other skin irritants, and this actually improves fish health and fitness. Now, what's crazy about this, though, is
Sharks,
this is,
the loofah of the sea.
Yeah, this is
Which
like
actually, that's where loofahs come from. Never mind.
no, they come from sponges, but that's okay. Also an animal, but they this, as far as these researchers know, is the only scenario in nature where prey seek out and rub up physically against a predator. So think about this.
Right?
The
Yeah.
cost-benefit analysis of this interaction has to be get eaten or live with parasites. I'm going to risk getting eaten.
Yeah. Okay. So
I've got an itch. I can't
behavior.
reach. Hey, bear, come here. Can you get my back right or just over the?
But the behavior that we're watching, though, it isn't like like you take a loofah and you scratch it back and forth and back and forth and back and forth, and you rub your skin and you
have hands.
You get in there. You have hands, but the fish are doing these quick bumps. They're very quick. They're not sustained. They're not like they could easily manage their speed to do some kind of forward, backward, exfoliating kind of moment. It's a quick bump. It doesn't seem like it would be.
It needs to be aggressive, maybe.
Yeah,
It doesn't seem like it would be enough to do much.
It's hard to get friction.
I don't know.
Maybe it's hard to get friction underwater.
So the other
You
thing,
have to really kind of.
the other thing about sharks, which kind of feeds into the conversation I was having with Justin a couple weeks ago about sharks, is that sharks get a pretty intense bad rap about being these killing machines and being very savage, but they don't constantly eat. And when they're not hungry, they don't eat. So this is, if you're also talking about the law of averages here and the chances of being eaten as a fish chafing up against a shark, it's out of the whole ocean. It's probably not that high. And especially if you're doing it in a pack of 100, your odds are even lower that you're going to get eaten. Right? So,
and I think the odds are outweighed by the need to do it. Like next time you have an itch, wherever the itch is, that's not important. The next time you have an itch, we're like, oh, I need to scratch that itch. Don't.
Wait.
Just don't. Just don't. And see how long you can last without going absolutely psychopathically insane.
Well, I'm hoping that that these researchers might work with physicists or materials engineers to see.
Loofah.
No, maybe make a better loofah. Yeah, no, but to see what kind of forces are going on during the quick fish bumps and see like what actually could be happening, because we can make all sorts of guesses about it, but understanding the actual physical forces that are involved and whether or not there's enough going on to really, I don't know, affect the skin of the fish in any way. I don't know. Maybe they're resetting their lateral line system. I don't know.
Oh,
yeah. I mean, that's a great question. I mean, the other thing to keep in mind, too, is the parasites that live on the skins of fish can be deadly. They can be a big problem. So to Justin's point, it's not even just that if you itch, you got to scratch it. It's that if you don't get rid of that skin parasite, it might kill you before the shark eats you. So it's in terms of like the hierarchy of importance, it might be worth the risk. But yeah,
Maslow's
I think
hierarchy of needs for fish.
Yeah, exactly.
Yeah.
So yes, like a scratching post for fish with force sensors on them, I think exactly would be the next step in research. That sounds great. Any PhD students out there, you're welcome. Go to University of Miami, look up this researcher, help them out.
This is This Week in Science. Thank you for listening to the show. Thank you for being here. Just another reminder that if you head over to twist.org, our calendars are now available. Click on the toad and order today. All right, Justin, what do you have?
Hey, thank me later if you're a future PhD student. Avoid the University of Miami. Turns out over the past 4 decades, the time between tropical storms making landfall on the Gulf Coast has been getting shorter and shorter and shorter. Predictions now by this new research published in AGU Journal Geophysical Research Letters suggest that by the end of the century, Louisiana and Florida will be twice as likely as they are now to experience 2 tropical storms that make landfall within 9 days of each other. This is according to the current model estimates of where we will be with global climate change. More tropical storms have been getting packed into single hurricane seasons already. Stronger hurricanes have been showing up. This is the season in the Gulf, southern coast of North America, which runs from June through November. And the time between them keeps getting closer and closer and closer. Florida and Louisiana, based on their modeling, are the most likely to experience sequential landfalls. What's where one hurricane moves over, devastates some infrastructure, does a bunch of flooding, a bunch of people are evacuating, and then within 10 days, it happens again. So part of the problems with that is, of course, there's not then enough time for infrastructure to recover. There's not enough time for things like overflowing water containment areas to rebound. You have soil that's already saturated with moisture. You have dams or rivers that are already near flooding because, of course, when one of those storms comes in, there's the initial damage of a hurricane hitting a coastal area, but there's an additional flooding and damage, levee breaking problems that occur as that storm moves inland and is filling up reservoirs and raising river levels even after the hurricane has passed the immediate impact zone. So this is according to one of the researchers, Daji Ji. If you need 15 days to restore infrastructure, for example, a power system, after a storm hits, and the second storm makes landfall before that system can recover, residents will face even more dangerous conditions. So, yeah, this was a study that examined hurricane seasons from 1979 to 2020, focusing on years in which at least 2 tropical storms made landfall in the same region within 2 weeks of each other, looked at how that number changed over time, paired that trend with a climate model to estimate how the number of back-to-back hurricanes would change over time, broke it down to regions, and found Louisiana and Florida, of course, most likely to get hit by this multiple strike event.
I'm just imagining how that would affect communities if, you've been hit once and then you don't have time to recover. How much of a reserve do you have to be able to exist in a place without power for how long?
Just happened
or if you
Texas.
have to leave. Yeah, or if you have to leave, you leave, and then when do you get to come back? There are huge questions for the habitability of these places moving forward long term.
Yeah, they had the Texas had the cold snap and then got hit by a storm, which was trouble. We've had Louisiana, I think, got hit by a hurricane, and then a year later, another one. Like, it's the sort of thing that's nature's way of telling you that it's mad, very angry.
Topography, like we were talking about before. It could also just be that.
It's topography.
It could also be
matched with climate change.
The way things move.
Yes, obviously the climate change, but the reason that there's uneven impacts is because of currents, both air and water, topography.
Actually, I think nature is specifically angry at both Louisiana and Florida.
No, it's not angry. It's just like, I didn't really want to give those up. I'd like them back underwater again.
Mm-hmm.
They were underwater for a very long time. It's not like,
Yeah.
They've been out of the water just for a little bit, and the water's like, no. I want you back. But yeah, it's not just Louisiana and Florida that this is going to potentially be an issue for. I'm sure this is just, a general, specifically those areas, but more generally, low-lying coastal regions that are within hurricane zones are probably going to be very likely to succumb to things like this.
Yeah, and then it becomes sort of like my, whenever there's a big, massive earthquake that devastates Haiti, I always make the point that this is, at this point, a man-made disaster. That you keep trying to rebuild someplace that is going to get knocked down again. How many times are you going to rebuild New Orleans? I mean, the beaches, the eastern beaches of southern Florida are completely artificial at this point.
Maybe Florida thinks it's Smash Mouth.
I don't even. Gets knocked down, get up.
I get knocked down, but I get up again. Yeah.
But I'm also.
That's not Smash Mouth. That's Chumbawamba.
Chumbawamba, isn't it?
Thank you. No, thanks. I don't know. Hey, look. We're having some sort of language difficulty here. There's actually a lot of tools researchers can use to trace the paths of humanity when we look into our ancient past.
Yes.
One of the oldest tools we've used is language. Since then, we have all sorts of archaeological, geological tools. There's genetics now. But they've made a discovery, basically, starting with language, a vast trans-Eurasian language family that consists of Japanese, Korean, Mongolian, and Turkish, which is sort of an interesting, as well as Tungu Isik, which I'm not sure where that is. These are languages that have had now their origins traced back 9,000 years to the early farming communities in northeast China. So until now, researchers had assumed that this language family had originated from Mongolia, because that's sort of northeastern China. About 3,000 years ago, this was spoken by horse-riding nomads who did keep livestock, but they weren't really farmers, crop farmers. And that these nomads had sort of spread this language around the region. This is Martine Robitz, the Max Planck Institute for Science of Human History, and Jenna and her colleagues used linguistic, archaeological, genetic evidence to conclude instead that it was at the onset of millet cultivation by farmers in China that led to the origin and spread of this language family. So one of the most important things is we've also seen linguistically in places along the Spice Trail, what have you, is where whenever people have to communicate over important things like food and water and trade, is where a lot of sharing of language takes place. And so the advent of agriculture means that you have all of this food being produced and you have this commodity that can now be traded and expanded elsewhere. And so the language around that then develops. Team did they studied linguistic features of languages using computational analysis to map their spread through similarities to each other. That also allowed them to trace Proto-Trans-Eurasian language back to that Liao River of northeast China around 9,000 years ago, which happened to be the exact same place that domestication of millet was taking place. So they didn't so much, they basically let's get all the data on the language and things that were going on, and it just correlatively, in a way, all lined up to tell the story. All these disparate pieces of information that they added up, told a nice narrative at the spread of this language, starting with early cultivation. Around 6,500 years ago, they also found descendants of some of these farmers moved eastwards into Korea, where they learned to cultivate rice about 3,300 years ago. And they also found genetic linkages from those people to Japan. Kind of an interesting thing. Robitz here says, we all identify ourselves with language. It's our identity. We often picture ourselves as one culture, one language, one genetic profile. Unless you're American, in which case you know all that's nonsense. Our study shows that like all populations, those in Asia and elsewhere are mixed. Pretty amazing that they were able to track down, spread of some pretty big languages down to a handful of farmers 9,000 years ago.
Yeah, I think that's like when you really take the whole story and put it in that kind of perspective of like the group of people trying to eat, to share their wares, to just get along, and like, okay, I got to get along with other people. Okay, we got to talk. And so the language spread, and the language was shared, and they moved, and eventually it becomes, a language of a nation, right? Of a
language of a nation,
people.
And also a massive human domestication effort.
Yes.
The early coinage, some of the oldest coinage that we've ever seen on this planet, has farming implements on it, because this was the most important thing. And we began to sort of subdivide human behavior the way that a farmer ran a farm. You have the farmer who's in charge of this stock, that stock, the other stock, and they all have to be regulated, treated differently, kept within fences, kept within boundaries. This is the formation of law, is basically farmer fences and how they treated livestock. Like,
it explains so much about modern society. I mean, really.
It does. Yeah.
Oh, you animals. What are we going to be up to next? Talk about some brains?
Mm-hmm.
Brains! Oh, that was last week.
Brains! Yes, I brought brains. Well, neurons in brains, really. There is a study out now that compares human neurons to the neurons of other mammals. Researchers have, from MIT, have compared human neurons across the mammalian kingdom, to originally stemming from an observation in rats that the ion channels in rats versus mice, that as the neurons started big, they started looking at the ion channel density. So ion channels are in the membrane of neurons, and when an electrochemical signal comes through, the ion channels will open to allow potassium and sodium move across the membrane to propagate current flow to create what we know as the action potential, like the individual electrical signal of the movement of a signal down a neuron. And so ion channels are essential for this happening. They had looked at all sorts of mammals and they're like, oh, ion density, that's great, whatever. But wait, looks like there's this difference between humans and rats. That's weird. I wonder if this difference between humans and rats holds up against other species. They looked at 10 different other species of mammals and found that as neurons get bigger, the concentration of ion channels in the membrane gets bigger as well. So there's a higher concentration. And the way that this turns out is that if you compare a chunk of brain from a rabbit and a chunk of brain from a shrew, the shrew brain being much tinier than a rabbit's brain, and so it's packed more densely and has smaller neurons in it, essentially what ends up happening is that for any unit area, any unit volume of brain across these two animals' brains, they have the same amount of ion channels. So essentially, it's like the neurons work with a particular function of the ion channels allow ions to flow and the action potentials to happen. Human neurons have fewer ion channels. Why? What they think. What? Yeah. It's like the only species. Human neurons have fewer ion channels. We still have action potentials. Everything works great. In fact, we consider ourselves like the smartest animals on the planet, thanks to all the ion channels in our brainy neurons.
So wait, you're saying it turns out we're the dumbest? Because, no, because I literally, like, I haven't read this story. I saw the headline and immediately made a biased assumption that it's like, oh, we have probably more ion channels than the rest of them. We have
fewer.
More. I know. I just assumed like our brains are like got more whatever the thing is that they're going to talk about because we're like so smart. We have fewer than the rest of all animals?
Well, not the rest of all animals. It's like the trend was an increasing trend, but our neurons do not follow that trend. Our like if you were to plot a line of neuron size to number of ion channels, you'd see it just an increasing line. But
from
you would have humans
to
be up at the top end, but below the line. Yeah. So what that means is that we have fewer ion channels for any volume of brain material. And the researchers think that what is happening is that because ion channels opening cause this flux of energy, the neurons then have to manage the ions. And so you have these pumps that you have to use ATP, the energy molecule for our cells to function. You have to use ATP to pump things back into the cell to keep these ion gradients going so that the neurons can be ready for the next action potential to come along. And to maintain neurons it's energy expensive. Our brains take a lot of energy. So they think that the human neurons came up with some other mechanism to increase efficiency so that they wouldn't have to, so that they get the same amount of electrical transmission, but don't have to spend as much energy to open and close those ion channels to allow that potentiation to happen.
So can I ask some really
I think it's
dumb
an energy
questions?
efficiency thing. Yeah. What?
Okay, so I'm going to ask a couple dumb questions. So based on this model, we don't have as many ion channels as we should have for the volume of our brains. But we know that our brains have grown quite a bit over the last, couple, maybe million years or so. So so there's probably, if you go back a couple million years to a erectus or a habilis or something, maybe it kind of matched what was happening with other mammals. But now we have a larger brain brain volume.
Yeah.
And now we have the same number of channels. So the brain biology had to figure out a workaround because we didn't develop the more channels. We just got more volume. Is that what I'm kind of hearing?
Right. So the researchers, they have a quote in this article here. We think that humans have evolved out of this building plan that was previously restricting the size of the cortex, and they figured out a way to become more energetically efficient. So you spend less ATP per volume compared to other species. And that implies that is what allowed us also to have these larger brains.
Because then that makes me think that if you took that ratio and put us back in line with any other of these mammals,
we would be dumber.
No, we'd have a much smaller brain.
But the next study that I did want to talk about was cool sponge study, sponge cells. Where did our nervous system come from? Sponges, they were the oldest organisms, super simple, right?
Just a tube.
It's a tube, right? It's just a tube and the water goes through it. It's like, and what does it have to communicate about? Well, it has lots of things to communicate about, apparently. So researchers publishing in Science over the last week found that sponges use an intricate cell communication system for feeding regulation. And it also allows them to weed out invading bacteria, which is exciting. So they are hypothesizing that this could help us understand how nervous systems evolved. So understanding that this cell-to-cell communication was occurring, they're able to determine that this could have been a predecessor. If you've got, one cell talking to another cell, this may have been that early state. They did X-ray imaging, electron microscopy. They looked at all these cool cells that were filter feeding and doing all this interesting digestive work. They had 18 different cell types. And they found that there are synaptic genes actually active in some of these cell types. Synaptic, synapses, neurons, zoop, zoop, talking to each other. So there are genes that we're still using today, genes encoding proteins that usually allow things like synapses to function, which is very cool. And then they determined that one of these cell types, They're calling it a secretory neuroid cell. We're getting so close to neurons here. It's fascinating. They send out arms, long arms, to grab choanocytes. And these choanocytes drive the water flow systems and help to capture the food. And so these neuroid cells reach out and grab onto them. And the expression of the genes and the chemicals, and they think that the neuroids are talking to the choanocytes and telling the choanocytes what to do to control the water flow, to help with the feeding, to make sure that everything is working the way that it's supposed to. But sponges,
That
more
loofah.
complicated than we thought.
Yeah.
More interesting than you thought. All right, my last story for the night has to do with pain. And, well, hopefully it will lead to this discovery will help us discover better treatments for chronic and spontaneous pain. So a lot of people with chronic pain will complain about the spontaneous shocks of just enormous pain. It's not the ongoing pain that you may feel, but these kind of bursts of pain that occur at regular intervals. These researchers publishing in Neurons this last week have determined that one of the things that's probably going on to cause these spontaneous bursts of pain is what's called cluster firing. So it's when a group of neurons, a cluster, fire together. This cluster firing in the dorsal root ganglia, which is, you've got your spinal cord going down your back, and then associated coming out the side of your spinal cord are these dorsal root ganglia. There's sets of cell bodies of neurons, and they work to connect your spinal cord to the rest of your body. And the dorsal root ganglia is important, but it's not supposed to get connections from sympathetic nerves. There aren't supposed to be sympathetic nerves growing into your dorsal root ganglia, but in the case of this spontaneous pain that occurs, that's what is happening. They have determined that there are sympathetic nerve fibers that are growing in to the dorsal root ganglia where they're not supposed to be. And then they seem to be stimulated by stress. So the sympathetic nervous system we associate it with our fight or flight system. So it helps us get ready to go and do things. The sympathetic nervous system is like, yeah, let's do stuff. Woo, woo. We're going to fight. We're going to run. So they think that it could be triggered by stress, by anger, by any number of kind of emotional top-down triggers from the brain. They could be coming down and stimulating these wayward sympathetic fibers that have grown into this root ganglia. And then they all go together and they fire up the dorsal root ganglia, which is then attached to all this other stuff. And then it's like pain in places where you shouldn't be having it. And it could be strangely sensory triggered, stress triggered. Because it's sensory neurons. The question is, where the sympathetic neurons, where is it coming from? But now they have an idea of what's going on. And so now can they figure out how to block it, how to stop it, how to keep this kind of pain from being ongoing? In their experiment, the researchers say that they were looking at mice, and the behaviors the authors measured in mice only happen about 8 times an hour. But could you imagine 8 times, even as just 8 times an hour, just these being racked by, spasms, sets of spasms regularly through the day? But in mice, they can see the spasms, but they can't ask the mice what kind of pain they're going through. Yeah. So they don't.
On a scale of 1 to 10 squeaks.
Yeah. Yeah. So the corroboration of the pain in the mouse model is still limited, and looking at it in people is definitely where they want to go. this has been This Week in Science. Are we done? Did we make it?
I think we did a tight 100.
Yeah, we did it. We did. Thanks, everyone, for joining us. It's been a great show. Good times. We love that you're here with us. And we do hope that you enjoyed the show. Shout outs to Fada. Thank you so much for your help with social media and show notes. Gord, thank you for manning the chat room. Identity 4, thank you so much for recording the show. And Rachel, thank you for all of your editing and your assistance. And I would like to thank our Patreon sponsors for their generous support. Thank you to Kent Northcote, Rick Loveman, Pierre Velazar, Ralphie Figueroa, John Ratnaswamy, Carl Kornfeld, Karen Tozzi, Woody MS, Andre Bassett, Chris Wozniak, Dave Bunn, Vegard Chefstad, Hal Snyder, Jonathan Stiles, a.k.a. Don Steino, John Lee, Ellie Coffin, Maddie Perrin, Gaurav Sharma, Don Mundus, Stephen Elberon, Daryl Myshak, Stu Pollock, Andrew Swanson, Fredis 104, Sky Luke, Paul Ronovich, Kevin Ridden, Noodles, Jack, Brian Carrington, Matt Bass, John Anina Lamb, Grant, John McKee, Greg Riley, Mark Hessenflow, Gene Tellier, Steve Leisman, a.k.a. Zima, Ken Hayes, Howard Tan, Christopher Rappin, Dana Pearson, Richard, Brendan Menish, Johnny Gridley, Kevin Railsback, Rami Day, Flying Out, Christopher Dreyer, Artyom, Greg Briggs, John Atwood, Hey Arizona, Support Aaron Lieberman for Governor, Rudy Garcia, Dave Wilkinson, Rodney Lewis, Paul Mallory Sutter, Philip Shane, Kurt Larson, Craig Landon, Mountain Sloth, Jim Trapo, Sarah Chavez, Sue Doster, Jason Olds, Dave Neighbor, Eric Knapp, E.O., Kevin Parachan, Aaron Luthen, Steve Bell, Bob Calder, Marjorie, Paul Disney, David Simmerly, Patrick Pecoraro, Tony Steele, Ulysses Adkins, and Jason Roberts. Thank you for all of your support on Patreon. And if you would like to support us on Patreon, make sure to head over to twis.org.
On next week's show,
We will be back Wednesday, 8 p.m. Pacific Time, broadcasting live on our YouTube and Facebook channels, as well as from twis.org/live.
hey, do you want to listen to us as a podcast? Maybe while you practice talking because you can't anymore. Just search for This Week in Science where podcasts are found. If you enjoy the show, you can get your friends to subscribe as well.
For more information on anything you've heard here today, show notes and links to stories will be available on our website, www.twis.org. Also, you can avoid signing up for the newsletter by not clicking on a thing there.
You can contact us directly. Email Kirsten at thisweekinscience.com, Justin at twistminion@gmail.com, or me, Blair, at blairbaz@twis.org. Just be sure to put TWIS, TWIS, in the subject line, or your email will be spam filtered to oblivion by being chafed by a bunch of fish until it is down to a nub.
You can also hit us up on the Twitter where we are at Twist Science, at Dr. Kiki, at Jacksonfly, and at Blair's Menagerie. We love your feedback. If there's a topic you'd like us to cover or address, a suggestion for an interview, a haiku that comes to you in the night, please let us know.
We'll be back here next week, and we hope you'll join us again for more great science news.
And if you've learned anything from this show, remember,
It's all in your head.
This Week in Science. This Week in Science. This Week in Science. This Week in Science, it's the end of the world. So I'm setting up shop, got my banner unfurled. It says the scientist is in, I'm gonna sell my advice. Show them how to stop the robots with a simple device. I'll reverse global warming with a wave of my hand. And all it'll cost you is a couple of grand. 'Cause this week's science is coming your way. So everybody listen to what I say. I use the scientific method for all that it's worth. And I'll broadcast my opinion all over the earth. 'Cause it's This Week in Science. This Week in Science. This Week in Science. 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 This Week in Science. This Week in Science.